Hello, everybody. I'd like to welcome you to the CMI webinar series designed by and for CMI. And again, this is a series, and it's great to have you back monthly as we continue building on this great body of knowledge. I'm Cynthia Howell, and I'm the Education, Training, and Outreach Manager, and I'm going to be the moderator for today. Want to tell you a little bit about our webinars. They are hosted by Colorado School of Mines and, of course, broadcast everywhere across the nation because that's where we sit as CMI employees. We would like for you to put forward any ideas that you have, what you'd like to see in webinars. Continue to feed that to us so we can continue to serve you through this webinar series. And this is a public webinar, and it's going to be available next week at ameslab.gov/CMI under the webinar menu on YouTube on the Critical Materials Institute channel. So we have two different places where it will be archived for your viewing later on. Questions. We are waiting, as usual, for questions to be answered to the end of the presentation. But again, we are using the Q&A box. If you would put your questions early in that Q&A box when you have them, that would be great so that we can be queued up and ready to go in the question and answer period. I would like to introduce our speaker today, Dr. Andriy Palasyuk. Reading things incorrectly here. He is a scientist too at Ames Laboratory. His PhD is in organic chemistry from the Ivan Franko National University of Lviv. He has areas of expertise in many different places, including materials discovery, development of novel cost-effective alloying approaches, and more. And he's been a part of Critical Materials Institute since 2016. He leads a comprehensive multi-institutional effort on the search for new magnetic materials and more affordable domestic alternatives for the existing rare earth containing permanent magnets. And I'm going to let him talk more about his incredible research. So Andriy, if you want to take it from here.
Hello, everyone. Do you hear me well? Everything works
Good.
Properly? Okay, so thank you for a very nice introduction. My name is Andriy Palasyuk, and as I was already introduced, I work with CMI for last more than 5 years, I think. And today I would like to talk about permanent magnets and about the problem which exists in permanent magnet world. And this is the gap magnet problem. So I will try to talk a little bit and to tell our story, how we attempted to address this gap magnet problem. So this is my outline of this presentation, and in the permanent magnet, sometimes it seems like we are looking for birds in the skies, because since 1980s, as neodymium iron boride was invented, there is nothing new. There is no new super permanent magnet. But if you look on the birds, it's important not only look in the skies for big birds, but also sometimes it is useful to look on the small birds. And what is important is not to observe the birds in the sky, but to have something already in the hand. And addressing the gap magnet problem is basically answering this question. So in my talk, I will talk about the projects which I am leading. I will touch a little bit about global market production of permanent magnets and about the process, how permanent magnets are done, I will talk what do we mean by gap. I will also then talk a little bit about the candidate which we chose to address the gap magnet problem, and what successes and challenges we met on that road. Then I will conclude and actually listen to your questions and try to address them too. So I'm a lead of CMI project 2114, which is a discovery project. And this is the multi-institutional effort where we in Ames do experiments. David Parker in Oak Ridge predicts and different permanent magnet possibilities and suggests to us as experimentalists what to do and how to proceed. And Valentin Tafur in University of California, Davis, is actually trying to find and collect every ferromagnet in the database, and actually also produce suggestions to the experimental part. And working together, we are basically approaching our problem with different prongs. We're trying to find the totally new materials. We are looking for the overlooked candidates. We are modifying what is already known, and we are trying to rehabilitate the materials which are almost ferromagnetic, but not. So, and by different influences of we can transform those materials into practical things. But today I will touch the blue prong. So a little bit about global market and about process of permanent magnets. And on this slide, you see that if you talk about permanent magnet market, you actually see only two candidates which are occupying almost the full circles. Doesn't matter either by market value or by production. Production actually is almost everything ferrite. For example, by value, market is divided by ferrites, between the ferrites and neodymium iron borides. There are also other candidates like ALNICO and samarium cobalt, but they are represented in very small sectors. And in fact, from these two circles, you can see that a huge gap exists between ferrite, neodymium iron borides, and all other representatives. So for some reason, globally, people decided to do basically just two permanent magnets. And they also decided to do them in almost in one way. Almost every permanent magnet which exists on the market is done by sintering. There is only one peculiar case, which is ALNICO, which is done differently. ALNICO is done through casting. So what is the gap? When we talk about permanent magnet gap magnets, we refer to the performance mainly. So it seems like there is two groups of permanent magnets. The one which performs from 0 to 10 megagauss-Örsted, and megagauss-Örsted is a measure of performance. And there is another group which is performing from 20 to 50 and above megagauss-Örsted. And there is a gap in performance which exists between 10 and 20 megagauss-Örsted. But this is not the whole story, because what is very important is how much everything costs. And if you look how much everything costs, then you have to take into the consideration material cost. You have to think about criticality, availability in the Earth crust, if you want, then you have to think about process cost, and you actually have to think about uninterruptibility and how to make the process never interruptible. And everything what I just said adds to the dollar sign. And gap exists between neodymium iron boride and ferrites. Those only two representatives which occupy the mass market, which I previously showed. Why are they occupying the mass market? Because their dollars per megagauss are acceptable for the mass market. And for example, for ALNICO and for samarium cobalt, for some reason, they are not that acceptable. And that's why those magnets, they found themselves in the niche market. So it is not only the gap in performance that exists, but there is also a gap in between the mass market and the niche market. So what do we want? What is uniting those two permanent magnets which are in the niche market? And what unites them is actually their value of dollars per kilogram per megagauss or stat. This value has to be $2 per kilogram per megagauss or stat, or it could be $10 to $20 per cubic meter per megagauss or stat. If you fulfill this parameter, there is a chance that you will be in the mass market. So now a little bit about rare earths and a worrisome future. If we look on the central image of this slide, we can see that it is predicted that by 2030, neodymium oxide and dysprosium oxide, two oxides which are used for producing neodymium iron boride, they will be short in supply. So demand will be much stronger than the supply. On the other hand, cerium and lanthanum are plenty. And I think these are the elements which have to be considered for permanent magnet development. So the idea would be, from the first glance, it seems like it's a good idea to take cerium, mix it with transition metals, which are also very abundant, and try to make a permanent magnet, or substitute cerium for neodymium or for other elements, and make permanent magnets more available, less expensive. So it seems like cerium is an excellent substitution possibility because it's abundant, domestic, and cheap. Except cerium is poor substitution possibility, because cerium is not a trivial element. It has a mixed valency problem, and with the mixed valency problem, always other adjacent problems appear. And if people substitute cerium for other rare earths, usually all magnetic properties, including Curie temperature and magnetocrystalline anisotropy, they degrade. And that's why cerium is a tricky element. With respect to transition metals, well, everything looks beautiful except cobalt is very valuable and critical. So it would be nice not to involve cobalt into the permanent magnet work. But nothing works without cobalt, or very rare things work without cobalt. So we decided still try to look on one of the classical compounds, cerium cobalt 5. Cerium cobalt 5 is a calcium copper 5 type compound, and from the literature we know that it's very good candidate for permanent magnet development, but for some reason cerium cobalt 5 is not a permanent magnet. So cerium cobalt 5 is an excellent permanent magnet material because it has large anisotropy, it has high Curie temperature, etc. But cerium cobalt 5, on the other hand, is poor permanent magnet material, especially from the perspective of cobalt content. And on the right side of this slide, you see the indicator, I would say, where you see how much cobalt you have and how many megagas it produces. So basically, it's cobalt which produces nothing. But we decided still, maybe we can do it practical. And everything changes if you admix a little bit of copper into cerium cobalt 5. So changes that make you amazed, because we grew single crystal of these types of materials, and we found that the crystal plate of 0.1 gram, basically 10 milligrams of the material, can actually hold 1 gram of the weight. This is what you see on the central image of this slide. This is amazing and not trivial, because usually single crystals don't have extrinsic magnetic properties. And even here already, we developed 6 to 8 megagauss or step. Extrinsic characteristics appear readily after the heat treatment. This fact alone actually attracted our attention very, very strongly, and for quite a bit. And we developed these single crystals and found, in fact, that we reached already gap performance, because this for example is already performing within the gap. It's more than 10 megagauss per step. What is even more interesting is that it has exceptional magnetocrystalline anisotropy, and the indicator which shows cobalts per megagauss per step starts to change. It's not that negative anymore. So we decided to figure out what is this? Why is it showing extrinsic magnetic properties? Why is it showing coercivity? And when we heat treated our single crystals, obviously we found that the grains or the material is not a single crystalline anymore. However, those precipitates which precipitated, and we thought that they are pinning sites. Unfortunately, there was no dependence on tantalum. Those precipitates, they were basically tantalum, or very, very rich with tantalum, but the magnetic properties were not dependent on tantalum. So we decided that this is just camouflage, if you want, or something that is showing that something is happening in the single crystals. They are degrading, or they are developing their subgranular microstructure, but in fact it's not a tantalum. So we decided, no, that's not a good result. We have to avoid tantalum, and we have to do something differently, so that we see the reason of the extrinsic properties by itself. And we decided to do alumina crucible synthesis, and we decided to test how much iron we can substitute into those 1,5 type systems. And as you see, the indicator is showing that we reached 13 megagauss per step, and we were able to reduce cobalt even further. Definitely we avoided tantalum, but results were very confusing again. When we polished our samples, when we did the XRD, we wanted to see the microstructure. We wanted to see what is responsible for the exceptional squareness of those hysteresis loops. And at low iron contents, we haven't seen anything. And at high iron contents, we saw already precipitation of secondary phase, but very disorganized. Usually if you have a very perfect squareness of your hysteresis loop, the microstructure should be very, very organized, very nice. So then we decided to look even deeper and found very interesting phenomenon. We found that after the heat treatment, single crystalline material primarily, or polycrystalline material, which develops large grains, within the grains, you develop stacking folds. And those stacking folds, they are very regular, very uniform, but not regular. Those stacking folds are actually insertions of 1,2 type structure between slabs of 1 type 5 material. So this is how they look and how they compare to the known crystal structures. But in contrast to those crystal structures, as I said, they are very uniform, but they are not regular, because in crystal in 5.9 or 2.7 or 1.3, they are regular. And we came to the conclusion that this must be the reason. So, but then I decided to go back to my experience, and my experience is till 2016 or 2017 was all about ALNICO. And ALNICO is one of the commercial permanent magnets. And this is one of the magnets which doesn't need powder metallurgy to develop extrinsic properties, because it develops its extrinsic properties through the spinodal decomposition. And the spinodal decomposition is intragranular process. So basically within the grain, within the singular grain, you develop your microstructure, and that microstructure is correspondent for your extrinsic magnetic properties. You don't care very much about grain boundary effects. And I thought, yeah, it is similar indeed. It is very similar indeed. So we don't care about the size of the grain. We don't care about, we care about size of the grain, but we want the grain to be large. And actually the whole process, which is corresponding to extrinsic properties, is happening within the grain. What does it mean globally? Globally, it simply means that it can be or has to be done or processed like ALNICO. So it has to be cast, and it has to be castable. That's a very interesting conclusion, and we wanted to test it. But if this is similar to ALNICO, then the temperature performance has to be similar to ALNICO. And indeed, when we measure temperature performance of coercivity, for example, versus versus temperature, we see that it's almost parallel to line, which is ALNICO line. So very different to other permanent magnets. Okay, that's very encouraging, and we decided to apply for funding to Department of Energy and convince them that they could help us test and scale up and see if the system is scalable. And we were successful of obtaining TCF award from Department of Energy. And this is a feasibility study of castability, scalability, and resistance to impurities of cerium gap magnets. And it includes two parts. It also includes Bunting Magnetics, Bunting Du Bois, American company, which is based in Du Bois. And they agreed to try to use this material for for bonded magnet applications. We will not talk about this part, but we will talk about casting efforts, which we did. It was successful. In fact, we were able to produce our material in one-step process, and we were able to scale up to 2 to 2.5 kilograms. So the process is done in vacuum induction melter in our Ames Laboratory Material Preparation Center. And as you see in the central image, you see the look on the alumina crucible after the synthesis. In fact, we have proven that this alumina crucible can be used repeatedly with the similar results. And this is how the magnet looks like. The permanent magnet looks like. And this is how it performs. And in fact, it outperforms the lab scale reference. And the indicator to the right already is not that negative after all. So we reached 15 to 16 megagauss or stat, and we are using less and less cobalt. So then let's talk about future prospective perspectives, if you want. We were very scared to approach the gap. Actually, we quite successfully passed already the gap, and we are thinking about now crossing the gap and performing over 25 megagauss or stat. And these are our preliminary results, in fact, which are showing that this is possible. And if we were able to produce on kilogram scale, similarly with similar method, our material, then the indicator of cobalts per megagauss or stat is becoming more and more positive. And in fact, we are starting to address the gap magnet problem. We can look on this magnet, on this system from two perspectives. We can look on this system from samarium cobalt perspective and from ALNICO perspective. Samarium cobalt is using expensive processing and has more than 55% of cobalt. If we imagine that our magnet is basically samarium cobalt derivative, then we reduce already cobalt to ALNICO levels, if you want, and we basically producing it differently. So we are casting. So we are reducing the price of samarium cobalt. But how about if we imagine our cerium magnet and improved ALNICO, for example? So if we say that our magnet is an ALNICO, so then now we have ALNICO with a huge coercivity. We have very strong ALNICO. So performance of ALNICO is very, very much increased. So in our case, we are creating the new mass market magnet. And this is achieved through the combination of novel intragranular magnetic domain pinning and simple processing. So with that, I wanted to thank Department of Energy, Critical Materials Institute, Ames Laboratory, everybody who one way or the other was introduced to this journey. And thank you for your support. And I'm ready to answer your questions.
Andriy, I'd like to thank you so much for a fantastic presentation. It is refreshing to see the work that you're doing with this gap magnet. And also the focus, as most of the CMI areas are, in trying to make it more affordable and available, in terms of the research that you're doing. And congratulations on getting to the point where you guys have proven the worth of this research and that you're crossing the gap. I think that's great and moving forward. and looking at this as being a mass market magnet. So, and great work here. I'd like to encourage those of you that are in the audience out there to prepare a question in the Q&A. And while we're waiting for a question, Andriy, is there anything else that you would like to say about your work and your team and where you're at?
So I'm in the Ames. My team, actually includes great professionals. I'm very enjoying working with Critical Material Institute because it's a very professional and collaborative environment. And actually, thankful. I'm very thankful to to support that Critical Material Institute and Tom Lagrasso and Helena always have in me and in our research, because sometimes it's not obvious at the very beginning how things will look at the very end.
Very, very true. It looks like we have a question queued up here.
So the first question I will read. The first question is, please comment on the thermal stability of the cerium-based gap magnets. As I said, and I showed already, maybe I can go back a little bit. This is, do you see my cursor?
Yes.
So this is the thermal performance of coercivity of two candidates. And as you see, it's very similar to ALNICO. It's actually very parallel to, or almost parallel to ALNICO lines. So it's a stable, thermally stable magnet. And for example, remanence temperature coefficient is minus 0.06 percent per degree Celsius, and coercivity is minus 0.13. So there is a table of comparison. So it's much better than neodymium iron boride, and it's very similar. It's not similar. It's better also than samarium cobalt. So this is the first question. Another question: what is the lowest content of cobalt you think you can get with 20 plus MgOE? I think we can get to 38 to 41 weight percent with 20 plus MgOE. So surprisingly, if we increase MgOE, we also decrease in cobalt, because MgOEs could be only increased with increased magnetization, and increased magnetization can only happen when you put more iron. So basically remove cobalt. Are there still inclusion secondary phases in the scaled up samples? How much control do you need over this for the end application, particularly with respect to stacking faults? That's a great question. In fact, we found, and actually it's presented here, that the perfectness of the microstructure is very crucial for the coercivity. For example, on this image, you see the more perfect the crystals, the microstructure is, the more well spread and uniform the stacking faults are. It is coercivity increases. So that means that controlling the heat treatment is crucial. How much control do we have? We are still developing that, but our casting experiments show that we can gain quite a bit of performance. So I don't see the all answers.
Okay, it looks like you have two questions left. One from Ivor Anderson.
Okay.
And Scott McCall.
Which do you prefer as a way to go to near net shape magnets, permanent mold casting or powder processing by metal injection molding? I think mold casting, because powder processing will increase possibility for oxidation, as well as you know, we will have basically all powder problems. So I think just casting, because the processing of this material has to be as simple as possible. Where the hysteresis curves you showed for the cast material, and if so, are you working on the net shape casting? Yes, I showed these. Do you see this?
Yes.
These are, in fact, hysteresis loop of cast material. So, and this is how it looks like. So you would wonder that how representative that is, but we claim that this is very, very representative, and the material is very uniform. Yes, I would like to work on the net shape casting, and we are working on the net shape casting. How do you control anisotropic direction, assuming it isn't isotropic? It's not anisotropic yet. Casting is not anisotropic. And how do I control? I want to develop the directional casting, because the casting that we have right now is not directional. And the curves, demagnetization curves that you see, they are from the wax aligned material. I hope I addressed all the questions.
Yes, it looks like we don't have any questions in the queue, but I'm going to leave it open here for a moment for a few more questions. We do have time. So anybody that's been wanting to place a question in, and we have one. Thank you. Oh, we have two.
Can you mill to get anisotropic powder and then use conventional techniques to consolidate? Probably not, because sintering was tried already in CMI, and if grains are small, it's very difficult to reach the performance which is reached through the casting. Maybe because if you have smaller grains, then you introduce all the powder problems or powder sintering problems associated. Can you mill it? Yeah, I think you can mill it, but again, consolidating the powder is difficult. Can you explain a little bit about the castability? What is extraordinary about that? You mentioned only ALNICO is made that way. Yeah, so castability is extraordinary because it's simple. It avoids crushing, and it avoids making small particles, and it avoids oxidation of the particles. And if you could do it in one casting step, then you avoid all the processing with powders. So, and since the coercivity mechanism here seems to be very similar, not similar, but kind of intragranular, so then it's possible to cast this material, and it actually simplifies the processing quite a bit. What is the energy product for cast bulk versus wax aligned material? I think the energy product for cast bulk would be 10 mGOE, 10, 11. But it depends how you measure, and you could be lucky and measure it along the from the grain which is aligned, and then there will not be a difference because grains of this material are large. The squareness of the second quadrant curve of the casting suggests that you have reasonable degree of alignment. Exactly. Are you chill casting? No, I am not chill casting. It's just melting in the alumina crucible. But alignment, you are absolutely correct, is coming from the microstructure, which is absolutely anisotropic and developing perpendicular to the easy axis. How about mechanical property of the cast material? Is it brittle? Unfortunately or fortunately, I don't know, it is very brittle. It is very brittle, especially if it's cast material. And the brittle it is, the more brittle it is, the more I judge that it is good material. Because we had a number of castings, and only the most brittle one, which cleaves, is very, very nice in performance.
Okay, it looks like we have all of the questions answered here. And just in case there are a few others, I'll keep this up. Oh, we do have one that just came in.
What is the grain morphology? Irregular shape. I can go back. Yeah, so this is a typical grain morphology. Do you see it?
I'm sorry, I think I took your share.
Oh,
your
you took my presentation back. So it's a large grain, but it's not like it's irregular, I think. I don't know how to describe it. There is nothing like specifically spherical or something. Are you saying that grain growth during slow cooling is what makes large lined grains? Yes.
Okay. I want to thank you again for a fantastic presentation on the work that you're doing with you and your team on gap magnets, so very important to all of us all over the world. So this recording, again, I want to thank all of our attendees and a large showing today. Thank you so much for being a part of this webinar. The recording is going to be available next week at ameslab.gov/CMI, and of course on our YouTube, the Critical Materials Institute channel. The next webinar is going to be on March 29th on the National High Magnetic Field Lab Rare Earth Initiative Project. This will be in the Critical Times as usual newsletter, and also on the social media for Ames Lab. If you have any suggestions for future webinar topic or presenter, please share it on the exit survey or email us at cmi@mines.edu. Thank you again for a great presentation, Andriy. And for the rest of you, again, we look forward to seeing you this upcoming month.